Hey there, Keys Precalculus. We're starting trig today, section 4.1, radian and degree measure. We went over most of this in class today, but I wanted to just reiterate it with you here on the video and work a few examples. If you will recall, in class we said that trigonometry means the measurement of angles. I'm going to read from your book on page 248. Initially, trigonometry dealt with relationships among the sides and angles of triangles and was used in the development of astronomy, navigation, and surveying. With the development of calculus and the physical sciences in the 17th century, a different perspective arose, one that viewed the classic trigonometric relationships as functions with a set of real numbers as their domains. Consequently, the applications of trigonometry expanded to include a vast number of physical phenomena involving rotations and vibrations, including sound waves, light waves, planetary orbits, vibrating strings, pendulums, and orbits of atomic particles. The approach in this text incorporates both perspectives, starting with angles and their measure, and that's what we're looking at today. If you will also recall, we talked about what an angle is. An angle is determined by rotating a ray, which is a half line, about its endpoint. So I've got this endpoint here in green. It's also called the vertex of the angle. We've got the initial side where it starts and it opens up or it rotates about this vertex. In this case, I'm going in the counterclockwise direction, which is the positive direction. And that opens up to be an angle. You are accustomed to measuring angles in degrees. That's what you've always done. And we take the degrees from a circle. I'm not going to review that because we did it in class and it's something that you already know. But we also learned a new measurement, a new unit of measurement called radian today. And a radian has to do with the radius of a circle. So go ahead and take a look at this illustration that I took from your text on the right here of the screen. This shows an angle opening up on a coordinate plane with a radius as this length of the radius here is going to be the initial side of the angle, and the terminal side is going to be another radius of the angle. And this angle that I was highlighted in red is called the acentral angle of this circle. And if I take the length of the radius of the circle and I create an arc length that is the same length as the radius. So arc length is going to be called S. R is radius. And if S, or this arc length, is equal to the radius, and a central angle opens up such that it cuts off an arc length that is the same length as the radius, then the measurement of that angle is 1 radian. 1 radian. It comes from the word radius. It's 1 radian. The definition in your book on page 249 says 1 radian is the measure of a central angle theta that intercepts an arc S equal to the length in the radius of the circle, R. Now we know that the diameter of a circle wraps around the circumference 3 times and some change. And because that change is an irrational number, 3.14157, forever and ever, we can't give it an exact value unless we call it pi. So it has been determined that the diameter of a circle will wrap around the circumference of that circle pi times, 3.14 something times, right? So if the diameter goes around the circle pi times, then the radius, which is half the diameter, will go around the circle twice that, or 2 pi times. And twice pi, twice 3.14, is 6.28, and so on. So a radius will go around a circle 6 times and some change, 0.28 to infinity. And so we're going to call that 2 pi to make it exact. And I added this figure 4.6 from your book to illustrate that. In general, the radian measure of a central angle theta over here is obtained by dividing the arc length S by the radius R. So you can find the measure of theta by taking an arc length S and dividing it by the radius, where theta is measured in radians. Because the unit of measure for S and R are the same, those units cancel each other out, so this ratio has no units. It's simply a real number. In other words, it doesn't matter if you're measuring the radius in inches or in centimeters or in feet or miles or whatever. When you divide the arc length, which is going to be the same unit, by the radius, you're going to end up just getting a real number. But we do say that theta is measured in radians, or theta will be a certain number radian. While we're on it here, I'm also going to show that by doing some algebra, multiplying both sides by r, we can say that an arc length is equivalent to the angle opened up times the radius, or theta times the radius. And we will be using that a little later on. But I just want you to see how the arc length, the radius, and theta all relate to each other. Now I want to take you back to how many times the radius goes around the circle, or actually I should rather say the different openings or the measurements of theta. If the angle makes one full revolution around the circle, in degrees we say it's 360 degrees, but in radians we say it's 2 pi radian. Theta would be 2 pi radian if you start here on the initial side and theta opens up and goes all the way around and its terminal side lands on the initial side. If it doesn't open up at all, then we would say that it was 0 radian. But when it opens up and makes one full revolution, it's 2 pi. And then we also talked about how when it makes a half a revolution, if it goes from the x-axis over here just to the negative side of the x-axis, 1/2 a revolution, it's half of 2 pi, which is 1 pi. If theta makes 1/4 of a revolution, then it will be 1/4 of 2, which is going to be, or 1/4 of 2 pi, which is going to be pi over 2. So it's going to be half of half, which is half of pi, which is pi over 2. And if it makes 3/4 of a revolution, it starts here, goes 3/4 of the way around, and lands here, then we're going to have 3 pi over 2 radian. That's how big that angle would be. And that's if the angle or the terminal side would land on one of the axes. But what if the terminal side landed in one of the quadrants? Don't forget we have quadrant 1, quadrant 2, quadrant 3, which y'all learned, way back when. And let's see if I can put quadrant 4 down here. Quadrant 4. So what if our angle landed in one of the quadrants? How are we going to determine what its radian is? Let's go over some of the most common angles that we will encounter in our trig exploration. Don't forget that 2 pi is 1 revolution. 2 pi radian is 1 revolution, which is equivalent to 360 degrees. Therefore, 1 pi is half a revolution, which is equivalent to 180 degrees. This second relationship is simplified. Therefore, we're going to use that as our ratio. So if we are trying to go from degrees to radians, we would take whatever our degrees are and we would multiply it by pi radian over 180 degrees. So I could cancel out my degrees and then just be left with radian. If I wanted to go from radian to degrees, I would take whatever my radian is, my x radians, and I would multiply it by 180 degrees over pi. Pi radian, I should say. So I could cancel out my radians and be left with degrees. These are simply proportions. That's why I can write them either way. I can write my proportion as pi radian over 180 degrees, or I can write it as 180 degrees over pi radian. I'm going to put on the denominator whatever I'm trying to change out of. If I want to get rid of degrees, I put degrees on the denominator. If I want to get rid of radian, I put radian on the denominator. Let's do this. For example, we did one in class, but I'm going to do it again in here. Let's say that the theta on here is 60 degrees, and I want to know what the radian are. So what I would do is I'm going to take my 60 degrees, that's my x, and I'm going to multiply it by either pi radian over 180 degrees or 180 degrees over pi radian. But because I want to get rid of my degrees, I'm going to put that on the denominator, and I'm going to put pi radian on the numerator. So here I can cancel out my degrees, and I can simplify this as 60 times pi over 180. And 60 over 180 reduces to 1/3, so this is really just pi over 3. So 60 degrees is equivalent to pi over 3 radian. We don't usually write the word radian afterwards, we just say pi over 3, and that's fine. So now let's do another one. Let's say I have an angle that opens up over here. So my theta, here's my theta, and I say that theta is 5 pi over 6 radian. Could I convert that to degrees? Well, sure I can. Say 5 pi divided by 6 radian is equivalent to 180 degrees over pi radian. I took that from this purple relationship that I wrote up here when we go from radian to degree. And I don't mean it's equivalent to, that should have been at times. This should be a times. So I said that wrong. I apologize. But anyway, so when we multiply this out, radian is basically on the numerator, so I can cross that out with that. Pi is on the numerator, so I can cross those out, get rid of my pi's. And now I can simplify 5 times 180 over 1. Well, divided by 6. Sorry, I didn't mean to say it that way. I meant to say 5 times 180 degree divided by 6 times 1. Okay, my denominator has a common factor with one of the factors in my numerator. So 6 goes into 180 30 times. So basically, I'm going to say 5 times 30, which gives me 150 degrees. Sorry I stumbled through all that, but that is how you convert radian to degrees. I would like you to finish converting all the degrees on your unit circle that I gave you to radian by class on Thursday. So you'll have two relationships there. Or not two relationships, you'll have two numbers for each of those special angles. It shouldn't take you more than about 5 minutes or less to do that. So have that ready for class on Thursday. Now we're going to talk about sketching and finding coterminal angles. So if you'll look on page 250 in your book at example 1, they are asking you to find and sketch some coterminal angles. What do I mean by that? Coterminal angles are angles that have the same initial side and the same terminal side, but different angle measurements. Because remember, an angle can open up, it goes in a circle, and a circle is infinite, so it can open up many, many times. It can open up in a positive direction, that means it's going to go counterclockwise, or it can open up in a negative direction, that means it would go clockwise. So let's say I have this angle theta that opens up to, see what I have here? 13 pi over 6 radian. Can you find a coterminal angle? And once again, by coterminal angle, I mean an angle like this green one, who has the same initial side as the red one and the same terminal side as the red one, but opens up to a different degree. How's that possible? Well, as we said before, it goes around a circle. So it has several rotations, and it can land in that same spot infinite number of times, just like we have 2 o'clock every single day. Actually, we have it twice a day. We have 2 o'clock in the morning and 2 o'clock in the afternoon. Same thing here. So I can either find a coterminal angle that opens up just a little bit, or I can find a coterminal angle that goes around one more rotation. Well, if it goes around one more rotation, I would be adding 2 pi. But in this case, I want to do this smaller angle here. I want to know what it is when it's within 2 pi, between 0 and 2 pi radian. Sorry. So in order to do that, I would have to take my 13 pi over 6 radian, and I would have to subtract 2 pi radian from it to get this little piece right here. So I would take this whole thing and I would take away 2 pi radian, and that would leave me with this green theta. So if I were to do this, I need to have a common denominator. So I'm going to change my 2 pi into 12 pi over 6, because 6 goes into 12 twice, and that gives me the common denominator with 13 pi over 6. Sorry. And so when I do my subtraction, 13 pi over 6 minus 12 pi over 6 is 1 pi over 6. So a coterminal angle with 13 pi over 6 is also pi over 6. Different angle measurement, different radian, but coterminal angles. So let's do another one. Let's say theta equals 3 pi over 4, and I said find another terminal angle. Or find a coterminal angle. I could go around, add 2 pi, go around 2 pi degrees more, one more rotation to land there, or I could go, let's try going in the opposite direction. If I go in the opposite direction and I say find angle beta that is coterminal with angle theta, how could I do that? I would have to take angle theta and subtract 2 pi to go all the way around to get to a coterminal angle. So if I were to write it up with the correct colors here, I would say 3 pi over 4, and I would subtract 2 pi from that because I'm going in the opposite direction and I've got to go all the way around from one end to the other. And when I do that, I've got to give a common denominator, so that would be the same thing as saying 8 pi over 4, because 4 goes into 8 twice, so that would give me 2 pi. So with my common denominator, 3 pi over 4 minus 8 pi over 4, and I am going in the negative direction, therefore it's going to be a negative answer, right? So 3 pi over 4 minus 8 pi over 4 is equal to negative 5 pi. Keep drawing the same line. Over 4. So beta is equal to negative 5 pi over 4 radian. That gives me another coterminal angle with 3 pi over 4. So let's do the last part of this example. What if I gave you a theta as negative 2 pi over 3 and I said find a coterminal angle, one that lands in the same spot? Well, I could keep going around in the negative direction, another 2 pi, so I would keep going that way, or I could go the other way, positive way, and say let my alpha equal that. So what would my other angle be? What would my coterminal angle be? Well, in this case, I'm going to add 2 pi. I'm going to take what's here, and I'm going to go around in the positive direction, like I've shown here, and add 2 pi. If I went in the negative direction, I would give another negative angle. But if I said I wanted a positive angle in this case, a positive coterminal angle, what would I do? Well, I would take my negative 2 pi over 3. I can write it up here. I hope it shows. 2 pi over 3. And I'm going to add 2 pi. But again, I need to have a common denominator. So this is the same thing as saying 6 pi over 3, because 3 goes into 6 twice. So when I add that to negative 2 pi over 3, what do I get? Well, negative 2 plus positive 6 is 4 pi. So I get 4 pi over 3. So alpha is equal to 4 pi over 3. Okay, so that's how you find coterminal angles. You either add or subtract a full rotation or multiple full rotations. But in this case, you're just going to have to choose to either add or subtract. So you can either choose if I give you no parameters, or if I give you some parameters, then you need to decide. If I say you got a negative angle, what's positive coterminal angle? Or if you've got a positive coterminal angle, what's a negative coterminal angle? Then you're going to need to figure out what to do. If I give you no other instruction, then you can either add or subtract as you would like. Okay, the last thing we're going to talk about are complementary and supplementary angles. Don't forget that two positive angles that are added to each other to equal 90 degrees are complementary, and two positive angles that are added together to equal 180 degrees are supplementary. If two positive angles are added together and they equal 90 degrees, those two angles are considered complementary. It can only be two. Same thing, if two positive angles are added together and their measures equal 180 degrees, those are supplementary. You know this from geometry and algebra. However, you also need to keep in mind that, and it shouldn't be however, in addition, you need to keep in mind that two complementary angles do not have to share a common side. They could be totally separate from each other as long as their measures add up to be 90 degrees. Same thing for supplementary. Two supplementary angles do not have to share a common side. They can be completely separate from each other as long as their measures add up to be 180 degrees. So how are we going to deal with it today? Well, instead of talking about degrees, we're going to talk about it in radians. How many radians is 90 degrees? Well, 90 degrees is a quarter of a revolution. A full revolution is 2 pi. A quarter of that is a half of a pi. So 90 degrees is equivalent to pi over 2. So I want to know if I could find two positive angles whose measures add to be pi over 2. Same thing for supplementary, but with a different number. You know that 180 degrees is equivalent to pi radian. Therefore, I want to know about if I can find two angles that add together to have to be pi radian. So let's do an example or two. So example in your book says, if possible, find the complement and the supplement of 2 pi over 5 and 4 pi over 5. So let's do the first one first. I did not mean to do that. Sorry about that. Video's a little rough tonight. Well, I guess it's always rough. But anyway, let's do the first one. Is there a complement to 2 pi over 5? Is 2 pi over 5 less than pi over 2? Well, yes. 2/5 is less than a half. Therefore, I can find its complement. How am I going to do that? I'm going to take 90 degrees, or pi over 2, because we're thinking in radians instead of degrees, and I'm going to subtract 2 pi over 5 from it. Now, I've got to get a common denominator for these two. So the common denominator would be 10. So 5 times 2 would give me 10. So this would be 5 pi over 2. And 2 times 5 would give me 10. So this would be over 10, but then I have to multiply that by 2, so this will be 4 pi. 5 pi minus 4 pi is 1 pi, so it would be pi over 10. So the complement to 2 pi over 5, I'm just going to put C here, is going to be pi over 10. Oh, that's a terrible 10. Sorry about that. Let's see if I can correct that 0 there. Looks like a 16. Okay, and let's go ahead and do the supplement then. Do the same thing, only instead of subtracting 2 pi over 5 from pi over 2, we're going to subtract it from pi. But I'm going to give it the common denominator of 5. So if 5 pi over 5 is equivalent to 5, is equivalent to 1 pi. And I'm going to subtract 2 pi over 5 from that. And when I get that, I get 3 pi over 5. So the supplement over here is going to be 3 pi over 5. I'm going to erase all this in a second, so just, if you need to study it, take a minute, pause the video, study it. Now let's do the same thing with 4 pi over 5. Can I find its complement and supplement? Well, first of all, 4 pi over 5 is greater than a half of a pi. Therefore, it has no complement. There's nothing I can add to 4 pi over 5 to get pi over 2. Therefore, there is no complement for here. All right, none. No complement. But there will be a supplement, okay, because 4 pi over 5 is smaller than 1 pi. So the way I'm going to do that is the same way I worked it before. I'm going to take pi and subtract 4 pi over 5 from it. But again, I want to have a common denominator. So I'm going to say 5 pi over 5 minus 4 pi over 5. Well, that pi should be up there. Sorry about that. Equals 1 pi over 5, or just pi over 5. So the supplement to 4 pi over 5, sorry, it's getting late and I guess I'm getting tongue-tied, is pi over 5. So that's how you work those problems. Okay, so I lied. I said that was the last thing, but actually I want to go over one more thing with you. And I also want to tell you that if you want more practice converting degrees to radian and radian to degrees, examples 3 and 4 on page 252 have some problems for you to work on. You should cover up the answers, cover up the solution, and just practice them and then check the solution in the book if you want more practice with it. But I want to talk to you about what angles in radian units lie in each quadrant. Okay, so if we're talking about the first between 0 and 2 pi, the first rotation of an angle in the circle, then the angles that lie in quadrant 1 range from 0, but it does not include 0 because 0 is not in quadrant 1, it's on the x-axis. 0 to pi over 2. The angles that lie in quadrant 2 go from pi over 2, not including pi over 2 because that is on the y-axis. It's a positive part of the y-axis. But it goes from pi over 2 to pi. Whoops. All right. The angles that lie in quadrant 3 go from pi, which is on the negative x-axis, to 3 pi over 2, and not including it because that would be the 3 pi over 2 is the y-axis in the negative direction. And in quadrant 4, the angles would go from 3 pi over 2 to 4 pi over 2. So this is 1 pi over 2, 2 pi over 2, 3 pi over 2, and the last would be 4 pi over 2, but we don't write that like that. We write it as 2 pi. Not including 2 pi because that is an angle equivalent to 0, or not equivalent to 0, but with the coterminal with 0, and it is on the positive x-axis. So these angles right here, 0 or 2 pi, pi over 2, 2 pi over 2 or just pi, and then 3 pi over 2 right here, do not lie in quadrants, they lie on the axes. You just need to keep this in mind as we study trigonometry. Become very familiar with it. It seems like common sense, and it is. But I just wanted to point it out to you. Y'all have a great evening.